Now if the, let's convert this into a line diagram. I have a column, I have a roller there, I applied axial force P, this X, that's Y, and this is Z. Okay. Now the question we are asking is a deformation of the form like this possible? Okay. If the deformation of this form, the question we are asking is if the deformation of the form like this possible. Okay. Now to answer that, what should happen? There should be a smooth displacement field from which you get the strain, then it has to satisfy the constellation to find the stress, and then you have to satisfy the equilibrium equations. Okay. If it deforms like that, it's like a beam bending problem. Okay. Even though we derived it for a case where it was subjected to pure bending moment, okay, we saw that the equation for bending, which was minus sigma xx by y minus y naught equal to mz by izz equal to e d square delta y by dx square, was for bending along the for bending deflection occurring along the y axis, right. Similarly, you add an equation minus sigma xx by z minus z naught equal to my by iyy equal to e times d square delta z by dx square for bending along the z direction. Okay. So basically now if it were to bend like this, this equation has to hold from the equilibrium point of view and from the strain, displacement, strain, stress, equilibrium equation point of view. Okay. So now the question is, what is this moment mz or my that is going to come in this problem? Okay. So let's go ahead, let's cut this beam somewhere here, okay, somewhere there, and write the equilibrium equation for that cut portion. And axial force P, since there is no vertical load applied, there won't be any shear force coming in the system. Okay. So basically I will have now the force P acting like this. If this displacement were to be absolute value of delta y, okay, without the sign, okay, that displacement were to be absolute value of delta y, then I will have moment P into delta y coming in the system, which is an anti-clockwise moment. So I should apply a clockwise moment here to counteract this P into delta y moment, which will be P into absolute value of delta y. P into absolute value of delta y will be this moment, mz moment. This is a mz moment. Okay. Now if it were to deflect up, then also say it didn't deflect down but it deflected up, add a P, it went up like this instead of coming down. Since we saw the scale go on either direction, then also I will have a P here, and there is this, let this distance be absolute value of delta y. Then I will have a moment. Now this produces a clockwise moment, so the moment that is produced mz, the mz moment would be like this, and this will be P into absolute value of delta y. Okay. Okay. Now going back to this bending equation in here, I now found mz for this system, so I use this equation to find delta y. Okay. So I use that equation to find delta y. So what is the equation I have? I have mz is E times izz d square delta y by dx square, which is nothing but P times absolute value of delta y. Okay. If I were to resolve the absolute sign, I am writing this for this case writing it for this case. Okay. Now delta y is negative. I want the absolute value of delta y, so I have to replace this with minus delta y, so that when delta y is negative, this equation gives a positive value. Okay. Now you find that the same equation holds for this case also, because this moment mz is a negative moment but delta y is positive. So when delta y is positive, this is a negative moment, so this gives the right sign for the bending moment. Okay. So this is the right expression of bending moment, whether it bends down like this or whether it bends up like that. Okay. So the equation remains the same. Okay. So now I have to solve this equation. Now what I have is, I have e I z z d square delta y by dx square equal to minus p times delta y. Okay. This I can rewrite it as d square delta y by dx square plus k square delta y equal to 0, where k is square root of p by e I z z. Okay. Now this is the second order differential equation for which the solution is known. Delta y would be of the form, c1 times cos kx plus c2 times sin kx. Okay. c1 and c2 are constants to be found from boundary conditions. Okay. Now you know that delta y is the simply supported beam that I am looking at. So delta y at x equal to 0, and let us assume the length of the beam is L. Okay. So you know that for a simply supported beam, delta y at x equal to 0 has to be 0, and delta y at x equal to L has to be 0. Okay. This gives you the condition that when delta y of 0 is nothing but c1, so c1 has to be 0. Okay. Delta y at x equal to L is c2 sin kl. This has to be equal to 0. Okay. Now you have two possibilities. One is c2 being 0 or sin kl being 0. Sin kl will be 0 if kl is n times pi, or n is an integer. Okay. From here you get that two solutions. If c2 is 0, the two solutions are delta y has to be identically 0, or it can be c2 times sin k is n pi x by L. Okay. If kl is equal to n pi. Okay. This is otherwise. Okay. 0 is when it is otherwise. Okay. Now let us go ahead and look at what this condition kl equal to n pi means. K, we said that k was square root of p by e I z z into L must be equal to n pi, implies p is n square pi square e I z z by L square. Okay. That is, if the load were to take this particular value, then an alternate solution arises, which is given by sin n pi x by L. When the deformation is given by, it is part of a sine wave. Okay. Okay. So this load is called as a critical load, PCR, and this expression is called as the Euler critical load, or another name given for critical is buckling load. Okay. Now what this means is, until P reaches P critical, this beam, this simply supported beam subject to an axial load will deform into this shape. It will expand laterally and contract horizontally. Okay. So this will be the deformed shape. Okay. If P is equal to P critical, if P is P critical, then an alternate solution arises, which is this, okay, which is that solution wherein this is given by C2 times sin n pi x by L. Okay. Still I have not determined what C2 is. What this tells us is there is no bound on C2, so it can continue to do like this. It can continue to deform like that. Okay. In particular, the mid-span deflection, which is the maximum deflection, is undefined, so it will continue to deform. Now, when it continues to deform, let us see what happens to the stress sigma xx. We did not use this part of the equation yet. We did not use this part of the equation yet, right. So, let us use that. Sigma xx is mz by izz minus into y minus y naught. Okay. This is due to bending. Okay. Now, mz is minus p times delta y into y minus y naught by izz, which is nothing but minus p times C2 sin n pi x by L into y minus y naught by izz. This is P critical. Okay. Sigma zz due to bending is. What is the net? Sigma axis would have two components, that will be a bending component plus an actual force component. There is an actual force also coming in here, right, because if I draw a free body diagram of this, if I draw a free body diagram of this structure, I will have a net P coming in there. I draw the free body diagram, I add a P, net axial compression, and a moment mz there. Okay. So, due to this moment we found what is the, due to this moment we found what is the stress. I have to add to that the stress caused due to this actual force P. Okay. That will be P by A, area of the cross section. Okay. That is going to give me sigma xx is P critical C2 sin n pi x by L divided by izz into y minus y naught plus P critical by area of cross section. Okay. Now, I can write izz as A times r square, where A is area of cross section and r square is radius of gyration. Okay. So, izz is area of cross section into radius of gyration squared. Okay. So, if I substitute that, sigma xx becomes minus P critical by area of cross section C2 by r square into y minus y naught into sin n pi x by L plus 1. Okay. Now, let us find what is the maximum stress now. The stress being given by here, sigma xx max will occur at x equal to L by 2, wherein sin n pi x by L would be maximum if n is an odd integer, okay, assuming n is 1 or assuming n is equal to 1. Okay. And then what you get is at x equal to L by 2, assuming n equal to 1, and y minus y naught is equal to y max. In compression, the maximum distance from the neutral axis to the compression fiber, which will be on the top usually. Okay. So, I will get sigma xx max as minus P critical by A into C2 y max C by R square plus 1. Okay. Now, as C tends to infinity, you find that sigma xx max tends to infinity. That is not possible, that will be a stress wherein this is like kind of a uniaxial state of stress, where you have the sigma axis varying like this. So, once this stress reaches, say you are doing it on a metallic steel rod which obeys von Mises criteria, okay, this should be less than or equal to sigma y uniaxial. This sigma axis max should be lesser than sigma y uniaxial, because this is like a uniaxial state of stress, and if you are finding the yield stress in uniaxial state of stress to be sigma y, this should be lesser than sigma y. Okay. So, basically now that tells you what is the maximum value of this, implies C2 must be lesser than or equal to sigma y uniaxial divided by P critical into A minus 1 into R square by y c max. Okay. Commonly it is attributed that the material failure is different from stability failure in the sense that it is independent of the material yield stress value, but the material yield stress value governs what is the maximum deflection that you can have. It is not independent of the material failure, but what happens here is because of the geometry the structure continues to deform, because you are writing the equilibrium equation the deformed shape. Okay, it continues to deform, or it has multiple solutions possible arising at a particular stress value, and that hence causes the stress to exceed a particular limiting value given by a material failure limit. Okay, it is not that stability induced failure are not material failures. Okay. Now, let us next see what value of n I should assume. Okay. Next is what is the value of n to be taken. Here I have taken n as 1. Let us say why did I take n as 1? Okay. What value for n? Okay. Now, this depends upon what is the mode of deformation that is possible for the structure. If I add just a simply supported structure, simply supported column with an axial force P applied, at a midspan can show any deflection that it wants to have, and it can deform in particular into a part of a sinusoidal curve. Okay. So, here n can be 1, or when n is 1, that results in the least value of PCR. Okay. This yields the least possible value for PCR, the critical axial load. Okay. If you recollect, we found PCR to be n square pi square E times IZZ divided by L square. So, this will be least when n equal to 1. Now, which means the body will fail when n is equal to 1 when this critical load is occurring. However, if I were to strengthen this structure at a midspan by putting some extra rigid supports, or I stiffen the member by providing extra plates at the midspan, this deformation is not possible, and what should happen now is it should deform into something like this, okay, which is when happens when n equal to 2. Okay. When n equal to 2, this happens. So, in that case, for this case n would be 2. Okay. If I were to put additional stiffeners at L by 4, L by 2 and 3 L by 4, then higher modes of buckling will occur. This shape that you get for the deformed shape, this delta y being C2 sin pi x by L is the first, is called as a first mode shape for the buckled column. Okay. C2 sin 2 pi x by L similarly is called as the second mode shape for the column. Buckled column. Okay. So, these are the deflections called as a mode shape and the critical load is called as a critical load. Okay. Now, I want to do some more analysis on this Euler buckling analysis. I want to rewrite this PCR in terms of a stress like quantity. Sigma critical would be PCR by A, which would be pi square E, I write it as A r square divided by A into L square. Basically, I have written the moment of inertia as area of cross section times the radius of gyration squared. Okay. So, what I did before. So, this will give me pi square E by L by R the whole square. Okay. Now, this L by R is called as the slenderness ratio lambda. This is lambda is L by R, this is called as the slenderness ratio. I was telling you at the beginning of the lecture that if the slenderness, if the beam is slender, if it is not stout, then it will fail by buckling, right. So, that is, this is a measure of the slenderness. Okay. This is a measure of that slenderness, which is length by the radius of gyration of the cross section. Okay. To be more specific, this is the radius of gyration of the cross section in the z direction. So, let us say Rg. Okay. Now, let us plot this sigma critical as a function of slenderness ratio lambda. Okay. Now, this will look like a curve as shown here. Okay. As lambda tends to infinity, the stress will go to 0. As lambda tends to 0, the stress will go to infinity. Okay. So, basically this is how the relationship between sigma critical and slenderness ratio is. This is given by pi square E by lambda square. Okay. This is how the ratio is. Now, you know that if the material were to compress, the critical load cannot exceed the yield strength of the material. Okay. So, if I mark the yield strength of the material by this line sigma y, then there is no way that if I apply on a stout column or on a column where the slenderness ratio is very small, it is going to get compressed and it is going to fail by yielding or by the failure theory that governs the compressive failure rather than by slenderness by deforming laterally. What I mean by this is, up to this regime the column is called as short column. Okay. A short column wherein this will won't fail by buckling or it will won't fail by bending, it will won't fail by delta y being non-zero. Okay. In the short column it will won't fail by generating a delta y deformation. It will have only the axial compression possible, there will not be a bending action coming in which will cause this failure. Okay. Axial compression will cause the failure. Once you cross this point, the mode of failure is governed by the buckling mode of failure or the stability induced failure, wherein the uncontrolled lateral deformation will govern this failure mode. Okay. So, this is what you have to understand. Okay. In a short column, the failure is by, if I have a bar, it will compress axially and it will fail in this mode. In this regime, where it is called as a long column, just like a ruler that I showed you, in this regime what will happen is the same column when subjected to a compressive force P will bend like this. Will bend like that and fail. Okay. So, that is how the long column fails. This is how the long column fails, this is how the short column will fail. Okay. So, the failure modes will be different for a long column and a short column. Okay. Now, in all this, if I were to look at the load versus delta y max, okay, what will this curve look like? We found that delta y is given by C2 sin n pi x by L. Okay. Now, in particular we are looking at first mode shape. So, this is C2 sin pi x by L. Okay. So, basically now what happens is delta y max would be C2, right, at L by 2 or at L by 4 or 3 L by 4, the delta max value would be C2. Okay. Now, what happens if I were to plot delta y max versus P is, we will get a curve something like this. It will be 0 up to PCR and then it will show some infinite displacement which is C2, which is an undefined parameter, until this reaches the C2 max that we found before from the yield stress value. Okay, that will be the C2 max that we found before, that will be a very large value of deformations. Okay. Now, if I go to second mode, then also it will be C2 max, but that value will be different from this value, it will show a much larger deformation. This is P critical 2, which is 4 pi square E by lambda square. Okay. This is P critical 1, which is pi square E by lambda square. Now, it will show a much larger deformation. Okay. So, this is how the deformed shape will look like, the mid-span deflection. But in our experiment with the column here, with the scale here, you find that the moment I apply some load, it deforms laterally. So, it does not agree with our analysis here. So, we will see what we have to do to accommodate the fact that the column begins to deform the moment I apply a slight load. Okay. So, that is something we have to do next. Okay. Now, we saw that the column can deform in either down or up, and the analysis remains the same right from the beginning. I told you it can deform like this, or it can deform, a long column can buckle upward. What this is depends upon the probability, depends upon what is the disturbance that is causing it to go from the equilibrium state to a unstable state. Okay. So, this is a random, so called random probability that it can go down or it can go up, but whether it will go along the, whether it will deflect along the y or z depends upon the slenderness ratio. Okay. We found that for a simply supported beam, the critical load is pi square E by lambda square, where lambda was L by R z, where it is a radius of gyration for I for the about the z axis. Okay. On the other hand, I can similarly define a radius of gyration about the y axis L by R y, this will be lambda y. Okay. The above expression is lambda z, where it is L by R z. Okay. Now, which one is more will determine, whichever is more will lead to a lower value of stress, right. So, if this is more, if lambda z is greater than lambda y, okay, then sigma critical for the z axis would be lesser than sigma critical for the y axis. Okay. If this happens, then since sigma critical along z axis is less, it has to deform along the delta y direction, it should show a delta y deflection. Okay. If it were sigma, if it were the other way around, if it were such that lambda y was greater than lambda z, then sigma critical in the y direction would be lesser than sigma critical along the z direction. This implies there will be a delta z deformation, because the axis about which the beam bends is perpendicular to the axis about which it shows the deflection. Okay. So, in all these cases we still assume that the bending equation holds for even this case, it is an assumption, but it is found experimentally that it is a good enough assumption for these problems. Okay. So, the direction of bending and the axis about which it will bend, you have to be clear, it depends upon which slenderness ratio is more. Okay. If lambda z slenderness ratio is more, it will deflect along the y direction, if lambda y slenderness ratio is more, it will deflect along the z direction. Okay. So, that you can visualize for the scale, you know that the moment of inertia about this axis is more, because it is this cube times this thickness divided by 12. On the other hand, if I add cross the axis oriented like this, it will be this cube times this thickness. Okay. So, basically now that is why it bends like this. If I apply axial load, it bends along this direction, because there is a moment generated along this direction in here. Okay. So, that is the reason why it bends like that. Okay. With this we conclude today's lecture. We will look at more different boundary conditions and how to model realistic columns in the coming 2 lectures. Thank you.